Hi, welcome back. We have one more piece here. We're going to keep talking about pseudo-inverses, and this part we're going to talk about calculating them with QR factorization. So let's kind of pick up where we left off before. I'm going to start with the left pseudo-inverse. So again, just to kind of refresh our memories, we have some matrix A that's m by n. M is greater than n, and its columns are linearly independent. I'm not going to write all that out again, but its columns are linearly independent. That means it has a pseudo-inverse, A plus, that is the inverse of A transpose A times A transpose, like this. Okay. Now, if we have the QR factorization of A, so let's say A is equal to QR, and let's take a quick aside here just to sort of refresh our memory. If A is tall and skinny like this, so here's our A, right? Then Q is going to be m by n also, and R is going to be n by n. Okay, so we end up with a picture that looks kind of like this. Here's our Q, and here's our R. Okay, each, right? So if A is equal to QR, then we can go ahead and insert that into this formula over here. Oh, actually, before we insert it directly in this formula, let's talk about A transpose A inverse. So A transpose A inverse is QR transpose QR inverse, right? And because okay, yeah, and then then we're going to say this is equal to R transpose Q transpose QR inverse, right? Just distributing the transpose there. And Q transpose Q, that's I. So this is equal to R transpose R inverse, like that. Okay. So now I'm going to kind of plug that back in over here. Whoops, and say A plus the A pseudo inverse is equal to A transpose A inverse A transpose, which is equal to R transpose R inverse QR transpose, right? And then because R's are invertible, these triangular matrices are invertible, we can distribute that inside there, and so we end up sort of flipping again, and we get R inverse, R negative T, the inverse of the transpose, and then here again distribute R transpose Q transpose. These two are inverses of each other, so they turn into I and cancel out, and we get R inverse Q transpose is equal to the pseudo-inverse, which is exactly the formula that we were using for regular inverse, right? So this is actually pretty nice, because it means that if we have some matrix A and we're trying to solve for a system of linear equations, we're trying to solve for some x, say, we can do the QR factorization, and if the columns of A are not linearly independent, then QR factorization will catch it, right? That's actually the first thing that we used it for, was checking for that linear independence. So we do QR factorization. If the columns are dependent on each other, then we can stop. If they aren't, then we get this factorization and we can solve the system. And you can solve these systems using that same backsolve process that we were using before. And if you want to actually solve for the pseudo-inverse, if you want to build the pseudo-inverse, you can do that just the way we talked about building the inverse before, right? We could say, that, we have R A pseudo-inverse is equal to Q transpose, and therefore for each AI, R AI, you're going to get some column of Q transpose. So maybe I'll put like a tilde on there to make sure that it's clear that it's the transposed Q. So you can solve each column of A and find the pseudo-inverse doing doing n back substitutions, just like you would with the other. Okay, so what about the right pseudo-inverse? So now let's look at the other case. So now we're going to say that we have some A that's still m by n, but this time m is less than n, right? And this time the rows are linearly independent. So the QR factorization only is going to work if the columns are linearly independent. So we need to do the QR factorization on A transpose. So we'll do the QR factorization on A transpose. Let's say A transpose is equal to QR. Okay. And then our right pseudo-inverse formula, and to me, like, so just to think about like how I'm remembering these. I remember it by kind of like reworking it in my head, that I know this has to be the identity. A plus has to be the identity. So I'm thinking, okay, I need an A transpose on the right. I mean, to start with an A transpose that will cancel that thing, and then I do AA transpose inverse, right? And that way I know when the A appears over here that I have the inverse of it ready to go, and I can cancel those out, right? So that's my, like, first of all, I don't think you need to like memorize this formula. Maybe you do. I haven't made the exam for this yet. So, but I wouldn't just like try and like memorize it as a fact in and of itself. I would just think about like what it needs to look like to be a right inverse of this thing, or a left inverse for the other formula, and sort of like it should only take you sort of a second to sort of refigure out and check how it works. Okay. Anyway, a little bit of digression there, but okay. So now we can do exactly the same. We can do exactly the same sort of trick here. A transpose, well, that's QR, right? And then A, well, that's going to be QR, oops, that's going to be QR transpose. And then A transpose, that's QR again, inverse. Okay, and then, so this whole mess here on the inside, we end up with R transpose, Q transpose, Q, R, Q transpose Q is the identity matrix again. So we are back to R transpose R, inverse, QR. And then, because these are invertible, we can say Q R R inverse, R inverse transpose. These guys cancel out. Q R inverse transpose, which is it's a different final formula that we get, if you notice, for the right pseudo inverse there, but that's okay. We can sort of express it in terms of this QR factorization, and since we're doing the transpose anyway, we can make use of this fact. We can make use of the fact that a pseudo-inverse transpose is equal to a transpose pseudo-inverse. So that was true for sort of true inverses, right? That A inverse transpose is the same as A transpose inverse. I encourage you to explore this with this one too, and see if it works the way you want it to work. But what that means is that we can do the pseudo inverse of the long skinny of A transpose, and then just transpose it, right? So yeah, this is the transpose of this over here. So that's nice. So we don't have to calculate it separately. We can take the transpose of it, and it will be fine. Okay, so this was how we are gonna. This is our sort of relationship between QR factorizations and these pseudo inverses. And I'm just going to sort of do one more kind of piece of summarization here. If you have some linear system, AX equals B, right? Then you can do that QR factorization, and if it exists, you will find X equals A plus B if M is greater than N. If A is overdetermined, then this will be a solution if it exists, right? And in the case where M is less than N, this will definitely be a solution, one of many. Right? Because remember we said overdetermined could be no solutions, underdetermined infinitely many solutions. But either way, the pseudo-inverse will find it for you. Find it for you if it exists, or find at least a solution for you if it's underdetermined. So that's nice. So now we've covered all of our bases now. We know how to solve systems of linear equations regardless of whether it's square, overdetermined, underdetermined. And in every situation, we're going to use essentially the same strategy. We're going to do a QR factorization and then back substitute to solve the system. So, there's a lot, but this is like I said, this is kind of like one of the big things that we were trying so hard to get to this whole time. We put a lot of pieces together for this, and we've done it. We can solve arbitrary systems of linear equations now in cubic time. Not too bad. So, good job. You made it.